Hello people. This class is going to be about expected value, which is in a very broad sense, basically saying what is like the average situation in if a lot of possible things could happen. For example, if you're rolling a dice at an average, what is the value that you get? That's somewhat what expected value would like. Um, Before we really get into stuff, let's just make a few definitions. Like when people teach all of this to me, I know that it's very boring, so I probably won't end up listening to it. So I'll try to keep this like short and simple. Um, there is a sample set, which is basically the set of possible outcomes when, let's say, you're doing some sort of experiment. Let's say you're rolling a dice. The possible outcomes is getting a 1, 2, 3, 4, 5, 6. You could be tossing a coin, then possibilities are heads or tails, etc. So you basically have a set of possible outcomes. So this is one outcome, etc. Right? And now the thing is, there are two options, right? Either when we're writing, let's say, probability of getting a head, let's say, is half. I don't know if it's an unbiased coin, then it's half. Probability of getting a head on a coin is half. Fair enough. But this is kind of an issue. You see, like being mathematicians, like people don't like putting English as like you want to reduce the amount of random English as much as possible. Probability of getting head is half. Is that like false? What am I doing? It could also be 0 or 1. Who knows? But the point I was trying to say is that people prefer math over here. So it's like if you have x equal 1, if you can write it as something like this, that's much, much better to people in general, at least math people. And so what you do is you define this thing called a random variable. Um, Again, this is like sort of a formal sort of this thing. We don't really care. But basically what a random variable will do is, it's like, let's say you call it x, and it's sort of like a function which starts from your sample set, that's its domain, and outputs to numbers. Like, I don't really care whether they're natural numbers or real numbers or I don't know, even complex numbers, like numbers. Um, and the idea is basically like, let's say your sample set is something like, it's a dice. So you could either get a 1 on your dice, or you could get a 2, or you could get a 3, you could get a 4, you could get a 5, or 6. And basically, a random variable will map each of these possibilities to just a number. So this becomes 1, 2, 3, 4 as expected. And like here, it's kind of obvious, but in some cases, this is like this random variable is a lot easier to deal with. Because, for example, if I do head and tail, so there the possibilities are like head, comma, tail. And now if I define random variable for head as like 1 and tail as 0, now this is kind of better because when I'm saying this, instead of saying getting a head, I can say something like px equal 1, where x is the random variable which uses this definition, whatever. So another point also of this is like you don't need to write getting ahead every time. Like you could have just defined that getting ahead is 1 at the start, and now you can keep using it. Another very useful thing about this is that let's say you want to do something like probability of getting even number on dice. Now, this is where it's starting to become informal, right? Like, this is not math. Like, I mean, you're writing English, that's not allowed. So what you do is, like, again, your sample set was something like 1, 2, 3, 4, 5, 6. And you map 2, 4, and 6 to 1 because they're even. And you map 1, 3, 5 to like 0 because they're odd. And now x is basically this random variable. Oops, I think
Mana korma itu dia.
yeah, sorry. Okay. Basically x is this sort of interesting random variable that takes 1 over even numbers. And now you can say px equal 1. this is the probability of an even number. And that's kind of nice way of writing the same thing. Also, one interesting thing we noted is that here all the answers are 0 or 1. Here also they're 0 or 1. Here they're not. Here they're like 1 to 6 or something. So whenever the answer is either 0 or 1, which is like a binary output, we call this an indicator random variable. Again, totally irrelevant and basically useless, but definitions are definitions, so we should just remember for the sake of. Yeah. So this is the basic idea. And now we define the expected value. So the expected value of a random variable, x, is basically in some sense, its average value, kind of, right? So here, there is like kind of a 50% chance that it's going to be a 1 and 50% chance that it's going to be a 0. So if you keep doing this, you'll realize that at an average, my answer is going to be half. Again, we'll put this all formally, but basically the idea is that instead of this, maybe if I had done something like these are also 1. So now it's like 83% of the time you're getting a 1. So it's like if you do this 100 times, then at an average, your average, like your thing will be close to 0.8, something like that. This is 5 by 6, by the way. Whatever, 83.3 bar. So yeah, the basic idea is this is kind of a weighted average, rather, is a better way of putting it. And this weight that we put along with it is the problem. Like the probability of getting a 1 here is 5 by 6. And the probability of getting a 0 is 1 by 6. And we use those weights nicely. So we make a formal definition, which will basically be something like this. You have E of x as sigma of I, and we'll assume natural numbers for now, like the random variable only takes like 1 to n, etc. But it doesn't really matter. I mean, you could probably define it using integrals, but that's like totally irrelevant here. Basically, what it ends up being is something like this. What this really means is like, okay, let's see this for a dice, right? On a dice, there's a 1 by 6 chance that you get a 1. There's a 1 by 6 chance that you get a 2. 1 by 6 chance that you get a 3. 1 by 6 chance that you get a 4, 5, and 6, right? So basically what this thing calculates is this into this, plus this into this, plus this into this, and so on, right? So what you'll end up with is like 1 by 6 times 1 plus 2 plus 3 plus 4 plus 5 plus 6. Here, you can actually just add up these numbers because like the probabilities are equal. But in general, the probabilities may not be equal. So you'll have to first do the products and then add them up. But okay, here you'll get 3.5. Yeah. And that kind of makes sense, right? Because the possible values in a dice, are like 1, 2, 3, 4, 5, 6. And at an average, you expect that, there's, it's kind of 3.5, right? Like probability suggests that it'll be somewhere in the middle. But that's only if there's equal chance of each of these happening. Suddenly, if I say that your dice is kind of cheating with you, so there's a 50% chance that you get a 6, and basically 0% chance that you're going to get a 1. Now everything is going to shift this way. So the expected value of the dice, the random variable or whatever, is going to be a lot higher. It might be something like 4.5 something, I don't know. And this is the basic idea. And why are we bothered about this? I think one of the cool reasons why we'll be bothered about this is what we'll do in the next class, which is the probabilistic method, which basically says that if the average value is 3.5, then at some point the random variable would have taken something that was at least 3.5. And that seems obvious, but it's like insanely useful. And sometimes they just ask you to, calculate the expected value of something. And that's not always trivial because sometimes there are just too many things. For example, if I give you 100 dices and I roll all of them and then I add up all of the values and then I ask you whatever, let's say there's a random variable which is defined as the sum of the values on all of those things, right? And I ask you E of X. Now, if you start calculating probabilities of each thing, like because there are 100 minimum value you're going to get is 100, and that happens with like 1 by 6 raised to 100 chance, 101 with like 100 times 1 by 6 raised to 99 into 1 by 6 raised to 100 only into 1. Yeah, whatever. So you're not going to be doing this. And for that reason, there are these, very cool ideas in expected value. One of them is called the linearity of expectation, which we'll be covering in this class. And then there is another very interesting idea of thinking of it as sort of a recurrence relation kind of thing. And that also comes up a lot. But we'll get into that stuff in just a bit. Just to clear the fundamental stuff, I
Hello.
hope everyone is clear with all that. Yeah, hello.
Yeah, what's there from like 101? Can you please explain that case? I understood that of 100. What is you just write above 101 there?
Yeah, so okay, don't get into too much of that combi stuff, but basically, if you want 100 dices to end up with the value of 101, then it's basically it's going to be something like 1, 1, 1, 1, 1, all ones, but the last thing is 2, or
Hmm.
somewhere in the middle there's a 2, everything else is 1.
Hmm.
So, like, to choose which position the 2 comes, there are 100 choices because it's basically going to be something like 100 factorial by 99 factorial 1 factorial if you can do that sort of combi stuff. And because everything is forced, like this can't have been a 3 or something, all of these things are forced. Don't get too much into the details. The point I was saying is that it's very messy. And like this is still doable. If you start trying to do it for like 300, you'll realize that there are almost like zillion possibilities of what could have happened.
Yeah.
So we're not getting into that. And for that reason, there is this thing called the linearity of expectation, which really simplifies our work and helps us solve this in a matter of seconds. In fact, like the answer for this, by the way, is 350, which is kind of what you expect, like 100 times 3.5, because in some sense, all the
Hmm.
dices are just rolling independently. So you should just be able to add them up. But this is actually very powerful, and here it's kind of obvious, but not always. So we'll get to that. By the way, any other doubts as to what all has happened till now? Like I've don't get into too much of these definitions and all. Like I just wanted them to be clear for the sake of um, basic understanding of what we're doing. Um, but we're not going to be using them as such. Like it's just for you to be thorough with what you learn. Okay, just as a quick exercise, let's figure out what's the I roll it. Okay, mm, yeah. Let's do a simple question. Roll a dice 2 times. Find the expected value of. I'm going ahead. I'm writing English inside this, so deal with it. Expected value of number of heads in the 2 rows. Given that dice is fair. No, what? I wrote dice. Sorry. I meant toss a coin. And given that the coin is fair, so there's 50% chance of getting a head or tail in each round. Number of heads in the 2 tosses. Yeah. Quickly. People can try this out. Okay. 1 is the answer we have received. Uh, and like this is like simple stuff. I just want to make sure that everyone is with me over here. So I'm just doing this for the sake of this thing. But basically, even if you want to list out everything, these are the 4 possibilities. If you think of the random variable, this is kind of your sample set, sample space. And your random variable here would be like 2 because 2 heads, 1, 1, 0. Total it up, 4. But actually each of these happens with probability 1/4 because half into half. And what you really want to be adding is this thing. So when you do it, you'll get half plus 1/4 plus 1/4 plus 0, and that comes to 1. Exactly. Yeah, and even if you use this sort of same idea as 100 into 3.5, like if you do it in one trial, h and t, the kind of expected value is like half, and in two it's become into 2. So it's working here also. We don't know if it's luck or what's going on, but we won't even get into that just yet. We'll do another question in fact. Okay, so this next question is quite interesting and non-trivial, and like most of the stuff you would have seen till now, like why are we doing this? This is like 10th grade stuff, or I don't know. But it's still quite interesting. Okay, this question is called mean time to failure. And there are multiple approaches to solve this problem. We'll look into multiple. But basically what the question says is that, okay, what's the best flavor text I can put this? Okay, let's say you're playing a game and yeah, you start at level 0, and like the probability that you proceed to the next level is p. So p probability of reaching uh, level k from k minus 1, and with the remaining 1 minus p, by the way, probabilities have to add up to 1. I hope that's not the problem. And like 1 minus p probability, you just die. So you reset in some sense. So the question here is, okay, we didn't really talk about time, but you can think of 1 second for each level. So the question is, how much time does it take you how much time does it take at an average to die? So what's the expected value of the level at which you die? So more formally, I can maybe define, let's scroll a bit down. I can like define a random variable which um, takes value if you die at level k, then the expected value of this thing is k. So I'm asking you for t of x. That's really our question. And this probability is given to you. So yeah, let's think about this. This is not trivial by any means. And in fact, if you go by the standard approach, it'll take you a lot of time to solve this. So yeah. And if people are like comfortable for me to just start with this, by dying at level k, does it mean that we can't move to k plus 1, or we can't move to level k? Whatever you want actually. Okay, let's say that you die at level k means you didn't get to k plus 1. So instead of getting to k plus 1, you died. Like, I mean, the answer will probably just change by plus minus 1. It's fine. But okay, actually, it might impact calculations if you choose for the hardcore method. But yeah, maybe in fact I should start at level 1 then. I don't know. Like if people have started trying to solve it with 0, it's fine. But I'm just changing it to 1. So actually, you could have thought of it as what the other thing. Okay. Yeah, so you start at level 1. So the minimum value of your thing is 1. And if you die at 1, the answer is 1. But if you go to 2 and then die at 2, then the answer is 2, etc. Yeah, probably level 0 is kind of not really a good idea. So yeah, I don't really care about the exact answer or anything. Like, it's going to be broadly equivalent. And yeah, okay, maybe we should put in like a time. So in like 3 or 4 minutes, I guess we'll start talking about this. For 3 or 4 minutes, people can just put their minds and maybe do some hardcore math if you are willing to do it. Or you could wait for the slick solution. Or maybe find the slick solution. The question is clear to people, right? Like if there are any other doubts in the question, I'll answer. Yeah, that is see, that's a fail-safe method. Like if this question comes to you in an exam, you get this series. Okay, I mean, let's just do it and get over with it. But yeah, the main idea here is that you can actually avoid the series by uh doing it the other way. But yeah, the series is not actually too bad because there's a like uh there is a very smart way of even solving the series, or yeah, or you can just use the standard EGP formula or whatever. Yeah. But yeah, for I guess I can just clarify the series thing right away because there's no real brains in that. Basically, we use the definition of expected value, which is something like E times probability of X equal I. And this basically means that um, what is the probability that you die at level K? First, let's figure that out, right? For you to die at level K, let's say die at level 3, you must not have died at level 1. You also must not have died at level 2. But then you must have died at level 3, right? And we multiply stuff because they're independent and so you can do stuff, but like naturally, right? Like it's kind of like a weighted sort of scenario that you get through this and that. So it makes sense that you have to multiply them. I'm not getting into too much depth of why exactly that should be true, but it makes like basic sense. So, and we also have to multiply by this factor of I. So you'll have 3 around it. Similarly, you'll get something like 4p into p into p into 1 minus p. And in general, you'll get something like um, n into p raised to n minus 1 into 1 minus. And you're basically sigmaing this for n. And this goes all the way till infinity. But it's like kind of intuitive that, if your probability is, let's say, half, then the probability that you stay alive till infinity is almost zero. Like it's in fact equal to zero if you do limit stuff. Because what happens is that the chance of you surviving 10 steps is like half raised to 10. So the chance of you surviving till infinity is like this. And like if you put any number which is in between 0 and 1 here, that always goes to 0 as n goes to infinity. Because like you can see that, right? 0 0.5, 0 0.25, 0 whatever, 125, etc. It's going to get to 0 eventually. Um, or rather, a better way of saying it is it's going to get arbitrarily close to 0. So the chance of reaching such a high number is 0. So it doesn't really make this diverge. And okay, also there is like calculus stuff that comes in here. Like to be able to calculate this, you also need to prove that it converges and stuff. But that's fine. Like uh, we're skipping a lot of basic details here because we're trying to look at the broader idea. And yeah, this is kind of a standard AGP because you take out 1 minus p outside, and basically you have this sort of arithmetic progression here, which is like just natural numbers, and you have a geometric, and they're multiplied together. And there are standard ways of doing this. Um, One slightly smart thing you could choose to do is uh, do something like this. So first of all, we're going to ignore the 1 minus p for now. We can just multiply by 1 minus p at the end. But yeah, the point is we're trying to calculate this. So let's try to take, we know how to do this. P raised to 0 plus p raised to 1 plus p raised to 2 all the way till p raised to infinity. Like this converges to, I should not write p raised to, what? This converges to 1 by 1 minus p. I hope people here are okay with that. This is fine, right? Like this is just standard geometric progression, nothing fancy. Also I could take p raised to 1 plus p raised to 2 and so on. And this series converges to p by 1 minus p, because in general it's like a by 1 minus r, where a is the first term, that's p here and 1 here, and 1 minus r is the common product. And also you could take like p square plus blah blah blah, then you'll get p square by 1 minus p, etc. And if you add stuff up, you'll realize that p raised to 1 appears 2 times as you wanted. P raised to 2 appears 3 times. If I add in a p cube thing here, p raised to 3 will appear 4 times, etc. So actually what we are looking to calculate is this thing. So that actually becomes 1 plus p square all the way by 1 minus p. And also we had this factor of 1 minus p. So that actually cancels out. So really what we're looking to calculate is this. Is it this though? Did I mess something up? Okay, whatever. I might have made some slight calculation mistake, but this is not really the point. This is interesting. This should not have happened. Have I messed something up, people? Or is this, maybe this answer is actually right? I don't know. Oh yeah, it's probably right. Yeah, okay. Yeah. So you get the answer as 1 by 1 minus p. And so, for example, if p was equal to, let's say, 1 by 3, so the um chance of going to the next level is 1 by 3, then you die pretty early, because you get expected value of the thing you die at will become like 2 by 3, 1, yeah, 3 by 2. And on the other hand, if I made this like 2 by 3, now you'll die at level 3, which makes sense. If you increase the probability of living, you die at a higher level at an average. So that's fair. But now the question really, okay, sure, I'll go over it. Do you want me to go over the logic part or this part? Oh, like, I mean, it's not too important, because there are other ways to do this as well, first of all, because what you could do is you can multiply, you can call this sequence S, and you can say S into P minus S is will end up being a geometric, and then you can divide by P minus 1 and stuff works out. So that's like a more standard way. This I thought is slightly nicer, so I just showed it. But basically what I've done is I'm adding up lots of geometric progressions. So this is the standard one, p raised to 0, p raised to 1 all the way. This is a by 1 minus r, so 1 by 1 minus p, because first term is 1 and product is p. Now I take the same GP, but now it starts with p raised to 1. And I add it in this sort of smart column type way. So now it comes out as p by 1 minus p. Next time I started p square, next I started p cube, then p raised to 4, p raised to 5, and so on till infinity. And all of these sums come out as 1p, p square, p cube, all divided by 1 minus p each. So if you add stuff up along the columns, you'll end up with like p raised to 0, 1p raised to 0, 2p raised to 1, 3p raised to 2, 4p raised to 3, etc. And that's exactly what we had here, np raised to n minus 1. And that's kind of a funny thing that it came out that way. And you do the stuff and it comes out as this nice value. But we're not really looking into too much of this, because this is the thing you should not do. Almost every question that can be solved like this can also be solved without this. So it's also a nice idea that if you're seeing that you're getting a really bad series, that's actually a very good sign, because that means there's going to be a very easy way to do it as well. And that's basically sort of based on this idea that um, whether you are on level K or you're on level, whether you're on level 2 or level 20, it does not really matter to you in terms of where you're going. Like whether you're at 20, still the probability of reaching 21 is still P. It's not changing. It's not like getting from 100 to 101 is a lot harder, which in games is and does end up being true. So it's not exactly a very fair thing. But here it's like kind of random. So that's sort of the idea for Markov chain. Again, I won't go into exactly what this is, but you can maybe read up later. Which Markov chain basically says I don't care about what has happened till now. I only care about where I currently am. And I haven't read up on these too carefully myself, so I may be messing up details myself. But the idea is that um, let's say you are at level uh, okay. So the idea is you define this thing as y. Let y be the expected value of my random variable, right? We don't know what y. I end up getting this end series immediately, so I don't know what special it is. Yeah. It's fine. Like don't bother about special stuff and all. That's all irrelevant. Also, I should be more careful. I should say the chat messages so that people in the recording can make out what was going on. But yeah, basically the idea is that you relate y to itself in some sort of magical way. And the way to do this is basically what happens at the start. At the start, either you just die off immediately, right? So there's a 1 minus p chance that you just die off. And in that case, you're doing 1 minus p into 1. And in the second case, and here's the magic. First of all, this happens with probability p. And now you can say that, okay, I'm at level 2, but does it really matter? It's like when I reach level 2, I can imagine myself being at level 1 and just starting the game from scratch. And so I know I will reach level y at an average. But because I was one level ahead of where I started off, I will actually reach y plus 1. And this will take time to sink in. Basically, the idea is that like if the average value starting at 1 was y, then starting at 2, the average value should lead to y plus 1. Because you've just added 1 everywhere. Like it's symmetric in some sense. That's what I was saying earlier in Markov chain too, that whether where you are, um, basically what all you've done to reach here does not matter. Only what is going to happen in future is what matters. So the idea is that you're saying y is equal to 1 minus p times 1 and plus p times y plus 1. And you've got a linear equation in y. And now you just solve it. You get y equal 1 minus p plus p plus py. And this becomes 1. You take this here. 1 minus p times y is 1. You get y equal 1 over 1 minus p, which is what we got here. And instead of doing bunch of sigmas, crazy magic, now I did it in one. And yeah, here actually our AGP was surprisingly simple. It's not even going to be this nice, I'm telling you. Like you're going to have crazy stuff like p by 2 raised to n minus 2 into p 1 minus p into n minus 1 sigma 2n minus 3. Good luck calculating stuff like this. But instead of that, I can reduce it to one simple linear equation. And yeah, I hope this is clear to people. I think I can explain once more exactly what really happened here. The idea was, okay, someone on chat. Yeah. So basically the idea is, let's see if there's some better way to put this. Okay, I am starting my game at level 1. And expected value in some sense is like the average, right? So if I play this game at an average, I will get to level 1, right? Now let's play an alternate game where you start at level 2. It's the same game. So what you can imagine is I've just added 1 to all of the levels. Uh, it's like I've just changed the name of the level. What was like earlier, I was calling that thing level 0. I told you that's irrelevant. Like it'll just change by plus minus 1. So I'm just calling level 0 level 1 now. Now here I'm just calling level 1 level 2. So what will end up happening is I'll call level y plus 1. Also, y need not be an integer. It's not like you'll actually reach level y. It's like you get the idea. Basically, you're adding 1 everywhere. So it makes sense that you'll reach level y plus 1 if you got to start at 2. So basically, if someone gave you a free start, that you have one, let's say, lifeline like in KBC or something, and you don't win with probability P now, you just always proceed to level 2, and then the real game starts. So now you will reach level y plus 1 at average because you have assumed that y is the average level you reach when you started power. And now it's just a game of this equation, right? Because there are two possibilities when you start up the game. Either you just die off with 1 minus p probability, in which the value of the random variable is exactly 1. Or the value of the random variable can be, or this is like expected value of the random variable is y plus 1 in these cases where you actually pass to level 2. And it's okay if this is not 100% clear just yet. We will do more questions on similar ideas. So it'll take time to sink in. But this is insanely useful. Um, Probably even, okay, linearity of expectation is even more useful, but this is probably the only thing you can compare to it in terms of its sort of magical use. And very few people actually are aware of this. So most people are like, okay, I see the AGP, I'm gonna do it. But very few people realize that there are these sorts of tricks over here, which can help you finish the question off in matter of seconds. Um, and yeah, in general, if you wanted to solve a question like this, the idea is going to be the same. See the probability of dying off on the first step. And if you don't die on the first step, then imagine as if the second step is your first step. So yeah. Okay, we'll do any other questions on this. If people have still not got it, it's you can Google up Markov chains. It's not exactly this. I'm actually not 100% clear on what exactly Markov chains were. There was a class I was going to attend on it, but I did not end up attending that. So, what like a very basic introduction that I heard on it was that it was this kind of thing where you don't care about what has happened till now. So I'm guessing that it's sort of similar or related to this. It may not be the exact same thing, but it's probably worth Googling. It'll be quite interesting. In fact, something I'll also do probably. Maybe I should have done that before the class, but it's okay. Um, yeah. So it's 7:43. Okay, that's good actually. I thought I might end up not having enough to do.
The time is running very slow today. Not kidding.
Everything's running okay, I think. Yeah, I'm just considering whether I should start off with the yeah, okay, maybe I'll define linearity of expectation too, and then we'll do problems that use both of them. Also, Pranav, I'll answer your question later on.
Yeah, sure.
Yeah. So this is really like this. If you found thing above as kind of magical, the thing that's going to come below is like, okay, actually this looks obvious, but it's not at all obvious, and we'll see why. And it almost feels like cheating when you use it on questions. So yeah, linearity of expectation basically says E of x plus y is E of x plus E of y. And okay, what the hell is x plus y now? Whoa, what is this? So basically what you're doing is, let's say you're not conducting one experiment, but you're conducting two different types of experiments. Like maybe both experiments are the same, you don't know that. But let's say there is like experiment one, which is basically like tossing a coin. So the sample space of that is heads and tails. And then there's a second experiment that's also going on, that's rolling a dice. So you could get a 1, 2, 3, 4, 5, 6. And now basically what X and Y, by the way, are still random variables. So basically X is going to be some function which maps heads to 1, tails to 0, let's say. And here, I don't know, it maps evens to, okay, maybe it just, no, okay, let's say it maps odds to 1 for a change, and it maps evens to 0, something like this. This, what am I doing? Yeah, this is Y. So how we define X plus Y is basically, imagine that you're conducting both of these and you're kind of taking like ordered pairs. Basically like you could get a head and 1. You could also get a head and 2. You could also get head and 3. You could also get head and 6. You could also get tail and 1. Tail and 6. So on, etc. And you map each of these 12 outcomes to a value. And not just any value, but you map it to the sum of this value plus this value. Whatever was, like if I'm trying to find head 2, I will map it to the sum of head and 2. So 1 plus 0, and this will become 1. On the other hand, I want head 1, that will become 1 plus 1, that will be 2. And if I am trying to do tail plus 6, that will be 0 and 0. So this will be 0. So you're kind of defining this random variable z, which we call X plus Y, which sort of does this weirdish thing, right? And it looks kind of stupid right now. And okay, first of all, what is the theorem really saying? The theorem is saying that the average value of this sort of z, the expected value of z, is equal to the expected value of x, which was half, plus the expected value of y, which was also half. So the expected value of z is actually 1. And you know, this is not trivial if you try to do this directly, because you'll have to do something like 2 into 1 by 12 plus 1 into 1 by 12 plus 2 into 1 by 12, and lots of cases, 12 cases. And you calculate each one, you'll do the sum, comes as 1. And yeah, another important thing to note is like you could have this 1 and 2 being the same experiment, X and Y being the same random variable. So what it would mean there is like, if you, that's actually exactly what we did earlier. Oops. Like if you're tossing a coin 2 times, if you're rolling a dice 2 times, basically now this is kind of like X plus X, because whatever was the value in one time and value in one time, if I add both of those, you get the expected value in 2 times. And you're saying that that value is actually just E of X plus E of X. So basically the rolling a dice 2 times my expected value, which comes out as 7. It comes out as 7 because it's like 3.5 plus 3.5, right? And this makes sense. Like rolling a dice 2 times, you don't roll it 1 time, 3.5 is the average, 3.5 is the average again. Total sum should be 7. Makes sense. But the issue is, this only worked out so well because we had this thing called independent events. And this is maybe something I should define at the start, but you people would have been like, why is he defining this? So maybe now it makes more logical sense. Basically, rolling a dice first time and second time, I can say are kind of independent. Like whatever I got on the second try does not depend on what I got on the first try. Like both of them are just irrelevant to each other. On the other hand, okay, maybe a more motivating example is something like this. let's say you have 1, 2, 3, 4, 5, 6. And we say, what is the probability of getting even? This is half, right? Because 2, 4, 6. And probability of getting odd. It's also half because 1, 3, 5. But probability of getting getting even as well as odd, that's 0. And that's okay, makes sense. But on the other hand, if I done something like P getting like 2 divides X and P that, okay, this is bad notation because it means something else. Let's say X equal 2K, X equal 3K, right? This one is going to be half, this one is going to be 1 by 3. And Px equal 2K and 3K, that's equivalent to being a multiple of 6. And that's 1 by 6 because only 6 here is multiple of 6. And you'll notice that half into 1 by 3 is 1 by 6. So that's actually how we define independent events, which is basically saying that if P, A and B is equal to PA times PB, then they're independent of each other. But if P, A and B, like here, is not equal to half into half, then they're not independent because getting even and getting odd are like related to each other. You can't get both of them, for instance. So yeah, here it makes sense because probability of getting a 1 here and a 1 here, basically you can say that's like 1 by 36, which is actually equal to 1 by 6 times 1 by 6. And it all works out properly. But linearity of expectation, the magical thing about it is that it works out even when the things are not independent. So even if you did something like that odd and even thing, it'll still work out. And that's kind of magical. And we'll see as to why it's just like almost like cheating in this next question, because there are things that you should not be able to do, but linearity just says you can do it. So yeah, this is the question we have now. Oops, this is quite big. Also, people are following, right? Is linearity of expectations basic idea clear with everyone? And like, what are independent events? We don't really need to know what are independent events because linearity doesn't care about it. But yeah, okay, good job, people. Yeah, this is our question. And again, there are multiple ways to do this. One is magic way, and others are all not going to talk. But actually, first we will see the not magic way so that it's sort of clear as to how we are getting there. Otherwise, you'll be like, what if you're lying to us? What if the answer is not actually that? And yeah, if you get the answer, just you can tell people. Let's see who gets it first. It's not a race though. Like, okay, Francis, you knew the answer or you just solved it? Okay, wow. Wow. Did you use linearity? Obviously. Okay, cool. But yeah, give this a try. Pranjal says the answer is 1. That may be wrong. No comments. So the expected value according to Pranjal Jha, be careful because not Pranjal Srivastava. I'm sure Pranjal hears that a lot. I'm sorry. But yeah, it's just 1 using linearity. Basically, the idea is you define indicator random variable. Like, see, if you're writing this in the exam, you can't just say 1 by n times n is 1, hence proved. You have to be slightly formal because you're using something so fancy. You need to be careful of what you're saying. So it's not really fancy. In fact, I will show you the proof of it, but it's quite not trivial. So you define an indicator, basically a random variable that takes 0 and 1. Xi is 0 if ith guy gets, oops, Gagu, gets his own hat, and 1 if ith guy, oh, sorry, doesn't get, doesn't get, okay, and 1 if ith guy gets his hat. And what we do is basically we claim that E of, if I define this number of men who get their own hat back, this thing has some random variable which is X. So you can say E of X is sigma E of Xi, where I is going from 1 to n. And basically what I'm trying to say is that if, let's say, first guy, seventh guy, and eighth guy got back their hats, then this thing is going to look like something like 1 plus 0 plus 0 plus 0 plus blah blah blah. Second, third, fourth, fifth. Let's write it down. Sixth. Seventh one is 1. Eighth guy is 1. And whatever. Like, people get the point. So this total sum is going to end up being 3 or whatever. And that's actually the number of people who got it. So it's representing the right thing. And each of these are actually insanely easy to calculate because the probability that you get back your own hat is like 1 by n, because they're n hats and you choose a random one. And this is n minus 1 by n chance. So expected value of xi is like 0 into n minus 1 and plus 1 into 1. And this is a good thing about random variables, that indicator random variables, that you can basically say that its expected value is the probability of getting 1, because the 0 thing just goes to 0 anyway. And this is multiplied by this probability. So what ends up happening is you get 1 by n plus 1 by n plus 1 by n times, and the total sum is 1. Yeah. So this is the basic. I'm trying to be as formal as possible while writing this, because if you're writing this in, say, an exam or something, you should know how to write it, because you can't say take each man as an event. Like, it's right. Nothing wrong with saying that, but it's always nice to be able to say stuff like this. Also, it makes you look cool. I read this, I think it was Evans, some handout, which said, why do mathematicians use sigma for sum? He said one is that, it makes simplification, uh, no, men being an event is fine, right? Like, uh, I don't know. It's not objectified. Look, no. I'm actually okay. Again, I should say what you said if I'm answering it. But yes. Anyway, what I was saying is, why do mathematicians use sigma? One is because it makes stuff a lot easier. You don't need to write n things. And second, because it looks scary for non-mathematicians. So our one job in life is to make life look as scary to people who don't know expected value. But yeah, there are other ways to do this. For instance, one thing you could do, and that also works out quite nicely, is this idea of double counting. So if you saw my lecture on double counting, congratulations. If you didn't, then please go see. No, it's fine. But I want to clarify one thing. Let's in fact take the case where there are only two people. So either person 1 and person 2 both get their own hats, or person 2, person 1 neither get their own. So in this case, you have like 2, in this case, you have 0. Average comes out as 1, as we have proven. So that's all fine. But this is interesting because, I mean, it's fair to say that the probability that you get your own hat is 1 by n. But if I did get my own hat, the probability that 2 also gets their own hat is no longer 1 by n. It's something else. In fact, here, if 1 gets their own hat, then 2 also has to get their own hat. So they're not at all independent, because 1 by n into 1 by n is not equal to Like, I'll put 2 here. So probability of 1, 2 should have been 1 by 4, but it's actually half because there are only 2 outcomes and there's 50% chance of this happening. So they're not independent events. So when you added up stuff, you said very aram say it'll be 1 by n plus 1 by n plus 1 by n. But these are not independent of each other. And that's magic, right? Because if one happened to necessarily has to happen. If one didn't work out, then 2 also cannot work out. But somehow, like all of your mistakes, they averaged out and gave a null mistake that your answer ended up matching anyway. And somehow this always works out in expected value using linearity. And we'll see as to why exactly the theorem is true quickly. I won't get into too much of depth because it's just 2 double sigmas and you're manipulating signs. Basically, what you're saying is ex plus y is ex plus ey. We want to prove this, right? So why not like just write down the actual definition? That'll look something like sigma I plus j. Have to make a double sigma I bearing j bearing probability x equal I and y equal j is equal to sigma I p x equal I plus sigma j equal j. Okay. This is what we have to prove. Sorry for my slanting way of writing it, but uh, I hope this is clear. This is just the definition, right? Because this double sigma is not exactly necessary. You can maybe write it as I comma j in 1 sigma, but we'll split it into the double sigma because that's nice. Basically, what's going on here is that yeah, I mean, like, I hope that, like, this is just the definition, right? Like, nothing fancy going on here as such. The point here is basically going to be we split this I plus j into 2 parts. So we split the left sigma into I p x equal I and y equal j plus double sigma j times p x equal I and y equal j. And the idea is because there are 2 sigmas, this one is varying over I and this one over j. This we can actually take I common from this j sigma because j doesn't really depend on I. And we can take this one out here. So you get sigma I times px equal I and phi equal j. And basically j is going to vary over everything. And you know y is going to be something, like it's got to be something. So this sigma is actually totally irrelevant and all of this is irrelevant because it's something like you're doing a way of putting this for the dice example would be something like x equal 1 and y is either 1 or y is 2 or y is 3, 4, 5, 6. You're adding all of those up. So that actually just becomes equivalent to this xp of x equal I. Because exactly one of these is going to be true and there is going to get counted and rest are anyway going to be irrelevant. So what you end up with is I times px equal I, which is this term. And here the smart thing is you can exchange the sigmas and do the same thing and you'll get this. Also this is wrong, so it's y equal j. So yeah, that's the idea of the proof. Like I know the proof does not help with too much intuition, and that's why a lot of people also skip it when. Yeah, exactly. Um, yeah, I mean, I've been trying to avoid algebra using all of these tricks, but if you end up trying to prove stuff, well, to be honest, I won't really call this too much algebra. In fact, this is sort of the idea in double counting, where you exchange sigmas. This is really the key step. I just glanced over it, but the issue over here you would encounter is you had sigma I, sigma j, and now you can't take j outside because like j is varying. But double sigmas can always be interchanged. Not always, but when stuff is finite, all that. You need to prove convergence type things, which we are conveniently ignoring, but it's fine. Isn't geometry just algebra? Oh my God, no, please, no bashing. Let's not do bashing. But yeah, like I would say this is the most important step of the proof. Um, because this is like the key idea that you can exchange the sigmas, and also quite not trivial that you can. And like the idea behind being able to exchange sigmas is basically you have a grid, and whether you're summing up it like this first and then like this, like adding up each row and then adding up these final sums, or you're adding up each column first and then summing up all of these, the final value is going to be the same because it's going to be sum of all elements. So that's the reason why we can exchange double sigmas. And that's kind of combi sort of idea, right? You're converting algebra to combi. I'm gonna be, everything is combi, nothing is algebra here. But yeah, this is the sort of broad idea of the proof. And now we're going to see how we can absolutely destruct various problems with these ideas. Um, yeah, and okay, a funny story about this problem is I was actually studying for my JE class, and they gave us this question. They hadn't taught linearity of expectation. And yeah, they tried to solve this question, took about 35 minutes to solve it. They solved the same thing in about 10 seconds with the proof. So yeah, that's yeah, and then I actually explained linearity of expectation to the entire class, and my sir was like, "No way, that's true. No, I've never heard of that." But and then he was like, "Are you sure this works for dependent events? Like independent makes sense." I was like, "No, it works always." So I don't think I managed to convince him, but I think later on he also read up a bit and realized that, oh my God, he was not saying random stuff.
I also used to think that narrative expectation was for independent events until the MBA class.
Exactly. Like it makes a lot of sense for it to hold for independent events, but the fact that it works always, it's like, when you use a method, people always warn you, be careful. If you try to use it in this scenario, you will fail. With linearity, there's nothing. You can use it whenever you want, however you want, it'll always work. Okay, you can use it however, but you get the idea. Like you can use it a lot more than other stuff. So yeah, let's solve this question. If people don't get this immediately, it's very saddening news. Because um, basically in one role, the expected value of the indicator random variable is p, because um, you get heads with probability p and tails with probability 1 minus p. And you add this up n times, you get n times p, hence proved. Or you could do what my JE class did, which is sigma n choose r going from 0 to n, and then 1 by, and then yeah, you also have a r because there are r heads here, into 1 by n, no, 1 by p raised to n. Yeah, calculate the sigma, because basically what this is saying, this is the same thing. Why this works is like, if you want to get r heads, basically it's sort of what I was telling earlier in that dice question, but there are only two possibilities now. So it's, sorry, why did I write 1 by p? Not 1 by, just p. Oh, not, no. Sorry. This is only for half. Yeah. It's like p raised to r into 1 minus p raised to n. Basically, this is saying that if you want r heads, that's equivalent to getting p r times 1 minus p n minus r times, and then arranging those heads and tails in one of n choose r base. And then this is your like in your expected value, you have I into P of x equal I. This thing is this, and this thing is, no, actually, technically, uh, this thing is just this, or no, it is the full thing. Yeah, and this is the R. So, I mean, even calculating this is not too hard, to be honest, because what you can do is this very smart thing of rewriting n choose R as n minus 1 choose R minus 1 into n by R. And now this R cancels. Um, and this n is constant, so you can take it outside. And what you're left with is kind of like a binomial expansion, except there's one p extra for no reason. So you take that also outside, and you'll get like the binomial expansion of p plus 1 minus p raised to n minus 1. And this will become 1. So you'll get np. Or you could be smart and get it in 5-10 seconds. Your choice. But yeah, I mean, even this one kind of teaches you stuff that you can do stuff. But if it gets any harder than this, then it's goodbye for this method. This technique is yeah, exactly. Like I can relate. Like I was seeing this in my class. Everyone is try harding that expansion. Come on, we can do it. And then someone is so happy. We figured out the trick. We did it. We got the binomial. Meanwhile, I'm just sitting and I know the answer. So yeah, that's one of the ways to kill a problem with linearity of expectation. Now let's try to do a question which uses both linearity and the equation idea we had seen earlier. And this one is going to be non-trivial, not like the one above where you just do n times p game over. So yeah, this one is actually fairly um, hard question. Not hard, but like whatever. Yeah, the question basically says a soda company inscribes A1 to AN. I'm gonna change this a bit. I don't really say numbers A1 to N, just say 1 to N, right? Does not really matter. Each of its bottles uniformly at random. What is the expected value of number of sodas you must drink to collect at least one bottle cap labeled with each of the numbers? Yeah. So basically what you're saying is you take a random drink. Let's say you get number 3. Now you take another one. Let's say you get 3 again. Then you take one, you get 2. You keep taking this until you have drunk at least one soda of each type. So what is the expected value of number of sodas you would have drunk by the time you had at least one of each type? And yeah, this is a fairly hard question. Like at least it's not looking like I can finish this in 5 seconds. But without linearity, I'm not even sure how I would solve this given infinite time. So this was infinite, no? Or am I misremembering? What was infinite? The numbers possible? Then the answer would also be infinite. What are you talking? Oh, the answer is infinite. No, the answer is not
Ah.
infinite. That's another question. That's another one. That basically says
Did you
that
just copy this from the worksheet? Because in his name, I only see from there, no?
what?
Did you just copy it from the MBLP set, the problem statement?
Like I copied the question, but then I, retyped it because I didn't
Yeah,
want
you
to
didn't
mislead.
change the name. Come on, you should have changed the name.
Why? Soda company is nice. I like soda companies.
Ines.
Oh, okay. Yeah, maybe I should change that, but I mean, it's fine. You deal with it. Also, who is Ines?
Bosnian girl.
Okay, makes sense.
Yeah, that is how I guess you just copied it from the P set.
Yeah, a lot of stuff I've just taken problems from that thing because they actually did really well. For people wondering what this is, it's like a handout which was released in Math Beyond Limits. It's not technically been released on their website, but soon enough it'll be there also, I think. So it'll be public, but as of now, like they've just released it to the participants, so I haven't. But it's not like I'm doing some scam by taking it because it's anyway going to be public soon enough, and it's fine. Okay, but people, any ideas? What can we? How do we start even? Like, what? Also, it's 8:15 already. Wow. Yeah, I thought. Yeah, I really overestimated how much I can do in one class. But okay, I mean, this is basically what I wanted to cover for tomorrow's thing. Double counting styled argument. Interesting. How would you do that? Looking for each number. Mm, okay, so let's say I, rather than each. Okay, so you're saying, um, yeah, but the point is, let's say I can find the expected number of steps in which I get bottle 5, right? And I also have the expected value of the number of steps in which I get any of them for that matter. But how do I get the expected value of number of steps in which I get all of them? Like, okay, first yeah, this is an interesting question. What's the expected value of number of bottles you need to buy so that you get one bottle of type K, where K is some fixed value. Let's say to get bottle 1, right? And to do this, we will use our magic equation, which basically says that either you get it on the first try with probability 1 by n, or you don't get it on the first try, in which case it's like you're starting from scratch, right? Like the bottle that is gone is gone. It's not helping you get your 1. So n minus 1 into n to y. This is equal to y itself. Is this clear to people why this is true? And this would give, by the way, the answer as n minus 1. So it will take you n minus 1 steps to get 1. But the sad news is, this does not mean that it will take you n into n minus 1 steps to get all stuff. What plus not into the middle there? Did I mess something up? Oh, yes. Sorry, of course. Yeah. Yeah. So unfortunately, this is not the answer. But there are two things here to answer. Why is this not the answer? In fact, the question is, why should that even be the answer? And secondly, if not, then now what? Yeah, so I think this looking for each number idea is actually really good because, um, it got us somewhere, but it didn't get us anywhere useful. Just, um, like we got that after n minus 1, we would have had 1. At an average, n minus 1 ke baad we would have 2 also, but that doesn't mean after 2 times n minus 1, you'll have both 1 and 2. It also doesn't mean that in n minus 1, you'll have both 1 and 2. So we're kind of stuck. So let's change stuff a bit. What we're going to do instead is, a common idea in not here, but in fact, entire combi is like n, take the variable and replace it by constants, small constants. So let's say n was equal to 1. Now the answer is just 1 because in one soda you'll have what you want. So E is equal to 1. Now if I make n equal to 2, the idea is that the first bottle I need, I can get in just one step. And now that I have got one bottle, there is one bottle left for me to get. How much time does it take me to get that one bottle? That is the question. So if anyone gets an idea on how to solve the thing for n equal to 2, go ahead. Or You can also unmute and talk, by the way. People are mostly messaging on chat, which is also okay. But if you can talk, that will also be good. Yeah, so the question right now is like, how will I solve it for n equal to 2? Okay, any guesses even on like what seems to be the answer for n equal to 2 or something like that? Anybody? Okay, let me give a hint. So basically the idea is that the, the first bottle you will get in one move. That could have been either one or two, you don't know which one. But you got one bottle. So all I need to do is get a second bottle. So imagine this was like heads and tails, right? And there's half chance of getting heads, half chance of getting tails. That's kind of equivalent to what's going on here also. Half chance of getting one, half chance of getting two. I've already got one, let's say, and I want to get two. So that's equivalent to this game. That I have heads and tails, and I've already got tails. So now all I want to do is keep playing until I get a heads. So what's the expected value of turns in which I get a head? If in that I add one, that'll give me the answer. Okay, so let's try to solve this mini question, right? You have a coin which can show heads and tails, and you keep flipping it until you get a heads. So what's the expected value of turns you need to? And now come on, we have to think of our, okay, so let's see how do we motivate the fact that we need to use equations. So if I try to do this brutally, like the normal sigma way, what I'll get is like k into half raised to k minus 1 into half. Basically, like if I'm getting the uh, head in the kth turn, that means that what must have happened is t, h, something like that. And probability of this exact string occurring is like half into half into half into half. 2 is Pranjal's answer. Great, that is actually the answer. And basically, okay, here we're sort of getting an AGP. And AGP coming in, okay, that means that there is some equation too. I'm not 100% sure if this equation thing 2000% times works, but at least I've never seen a place where an AGP works, but equation doesn't work. So what you do is you define x as this value, and either it works out in the first chance itself, which is with probability half, or it doesn't work out in the first chance. That's also with probability half. And now you're just starting from scratch. So it's half into x plus 1. Okay, a big chat message. Time to read. If you view this problem as getting each bottle as a level. Oh, okay. Yes, 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 yes. Very good. That's going to be our idea. I'm not reading the full thing out just yet, but that is the exact idea. Yeah. So, okay, just solving this for the sake of this thing, you get half x equal 1, so x equal 2. So this expected value is 2. And also we have to add 1 because first it takes you one try to get the tail or get the head, but then you would be looking for a tail. So it's equivalent. And then it takes you at an average 2 more tries. So the answer is 3. And be very careful here. We have actually used linearity of expectation without realizing that we were being so careless. When we said that we can do 1 plus 2, 3, that's actually saying that expected value of number of turns is actually expected value turns. Let's say expected value of turns to get all n is expected value of number of turns to get the first one plus expected value of turns to get the second one plus expected value of turns to get the third one and so on. This is basically what we are saying in some sense. Like here, what that meant is expected value of number of turns in which you get both is the number of turns in which you get one, which is just one, plus the number of times turns in which you get the second one, which is two. And you can add them up by linearity. Yeah, exactly. Exactly what you were also saying, Kishan. The idea here is going to be this. And it turns out that calculating each one of these independently is not that bad. For example, basically what this will mean is if you have already gotten k heads, k of the numbers, and you're looking for a k plus 1th number. Yeah, I think the explanation, if I had known linearity, I would have got till here and thought I can't. Yeah, exactly. You can't sum up, but yeah, you can sum up. That's the cool part. And yeah, I think Kishan gave a really nice explanation as to this. Basically, it's like going from the kth to k plus 1th. You can think of it as a level, right? This is a game, and to get the k plus 1th, it's getting harder and harder because here, like first one you got almost trivially, but the second one took you 2 tries. And especially if you have n minus 1 already and you're looking for the nth, then there's very less chance that in the first try itself you will get this guy. In fact, it'll take you a lot of time for you to finally get that time. So it's taking you a lot more time to reach the next level every time. So basically the question is how much time does it take you to go from this kth level where you've got k of the numbers to the k plus 1th level? That's our question. And the idea is that, for this, like, because it's without loss of generality, we can assume that 1 to k we already have these. And we're looking to get 1 out of k plus 1, k plus 2, all the way up to n. Like, if we get any of these, let's go. Otherwise, sad. So, yeah, now we need to figure this out. Any ideas, people? Also, we're sort of running out of time, so this will probably be the last question. Maybe I'll give one sort of homework question. Doesn't have to be homework. You can choose to do it or not, but we'll have a class tomorrow also. So maybe at the start of the class, we can discuss it up. If I have any such question, if I don't. But yeah, again, when in doubt, go back to the basic definition. N minus b is the probability. Yeah, yeah, it's kind of looking dirty, but we'll see that it's not that bad. So we go back to the definition, right? Sigma r probability that you don't get anything for the first r minus 1 turn. So you're doing this r minus 1 times and it's repeatedly giving you a bad number, which is one of these, which you already had. And you're like, why? So k by n raised to r minus 1. And finally, it gives you n minus k by n. on the rth term. And we see AGP. So the first thing you do when you see AGP is cancel it and think, okay, so either we get it on the first try or we don't get it on the first try. No, I don't think the answer is k plus 1, Pranjal. I'm not in, I think the answer is something like n by n minus k or something. I'm not fully sure. Yeah, I think it's n by n minus k. We'll check. It's not that long. The expected value of x is like y, let's say. And so the point is basically either on the first try you get it, which happens with probability n minus k by n. Probability that you get one of these guys, right? Into 1 plus, you don't get it on the first try. Okay, that's kind of sad, but we can still keep trying. And yeah, now we go back to the same idea, right? You have now reached the second try and you're starting from scratch. So if from 1 it took you y tries, from 2 it will take you y plus 1 tries in some sense. And I think now people should start getting the hang of what's really going on in that sort of thing. Why this is y plus 1. And if not, I can try and explain again, maybe after I finish, because we're also sort of running out of time. But yeah, the idea is that whatever, you do the math, this becomes y n minus k by n, y is equal to 1, and you get y equal n by n minus k. So basically this is saying that if you have already k things, then the time you take to get the k plus 1 thing is approximately this much. And this makes sense because at the start, when k is 0, it takes you nearly no time, like 1. But then it starts increasing. It becomes n by n minus 1. And towards the end, it becomes like n. So, yeah, this is really the value of the thing. Okay, no problem. Basically, yeah, you'll end up getting something like n by n plus n by n minus 1 dot 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 n by 1. Don't add in n by 0 because then you'll never get an n plus 1 thing because it doesn't exist. But yeah, this is actually n times the harmonic number because you can take n common and that's the harmonic. And if you're looking into, sort of statistical kind of bounds, harmonic number is kind of around log n. So you can say this is around n log n. So it takes you like n log n time, kind of, to get all this stuff, which is actually quite nice, to be honest. Like n log n is very decent. Yeah, that's sort of the idea. If people are confused about the equation part, is that if n is large? No, actually this bound is actually very sharp. Not log, you'll have to take log base n here. So I think it's something like log n plus 1 and log n the whole plus 1. Harmonic number lies this range. I think. I can check out on Google, but yeah, it's actually very sharp because this is like almost equal. I mean, it's not equal for sure, but yeah, close to. And yeah, basically, formal way of putting that is if you do harmonic number divided by log n, the limit as n approaches infinity is 1. So yeah. Yeah, I think that's pretty much it for what I have today. Maybe I'll give in a question so that people can try. I'll give it two. The two ones I was actually going to do. Uh, we'll, it's fine. Like, don't really need to do them. They're all of the same idea. They'll be good practice if you're looking to get more familiar with this idea. You can try it if you want. They're here. You can take a screenshot if you want. If any doubts, now's the time. Yeah, second one is HMMT, you're right. In fact, it also appeared on math counts. And the super cool thing is that Luke Robitaille was the one with the question. And before the question began, in like 5 seconds, not even 5, like 2 seconds, he's like, boom, answer. It's like godly. Like I'd barely seen that the question has just come up when he's already answered. So yeah, and like linearity allows you to do that because like with linearity, this is that kind of 5 second question. Except it still requires you to use your brains, unlike that NP, which is like totally sad. But yeah, linearity does magic stuff a lot. And tomorrow's class is going to be about this thing called the probabilistic method. I spoke about it at the start and just say it again. Basically, the idea is going to be that if you get the expected value as 51.5, at some point it must have been at most 51. And at some point it must have been at least 52. Like kind of pigeonhole principle, but some sort of generalization to it. And yeah, exactly, pigeonhole, but a generalization. And pigeonhole can't solve everything. Expected value can also not solve everything, but can solve a lot more stuff. Um, and yeah, probabilistic method is like super, super useful, not just in Olympiads, but like if you open any random combi research paper, there's a 77% chance that you will get probabilistic. You know, I read some article which says that if you add in a statistic, people are 83% more likely to believe you. If you got that joke, then good. um, but yeah. Okay, cool. Yeah, I think you can stop recording, Pranav.
Yeah,
If
okay.
anyone has any doubt which is worth putting on recording, you can ask. Otherwise, you can also ask after recording has ended.
Should I stop it or not?
1 second, one. Okay, nobody seems. Oh, okay, yes, sure. Stop. Also, Pranjal,